Heater in the car. The engine is your source of heat, but you want to heat the cabin and cool the engine in the process. So thinking about what are the things you might have to think about to have heat source that you don't want to get too hot, cooler environment next door that you want to warm up. And then water flowing through the pipe where it's flowing but then at one temperature and then it hits a warmer temperature, and then presumably we would be thinking about the temperature after that, like how much it warms up and then how that continues on. So those are a few ideas. What are some other ones before we dive into these? What are some other ones? So I didn't get, these are, so Neely and Nicely, I think. Did you send me some?
Mm-hmm.
Oh yeah, you did. It was Andrew and Nicely.
No, I didn't.
But anyone can jump in if you have ideas.
Question, is it the friction on that's causing the heat in the slabs?
I think we're not there yet. We're going to talk
okay.
about that stuff. So,
Gotcha.
This was the posed question, and I just want us to pose a few more before we dive in. And then we're going to split up into teams of two and choose one to kind of start brainstorming what assumptions we might make towards solving these. And fine-tuning what the question is, because sometimes that's something you have to be careful about.
So most of our questions, we're looking at heat flow and transfer primarily, right? In this conservation of energy.
Conservation of energy, yeah. And that could be, so the one thing that I did notice was that these top three, for the most part, are time-changing temperatures. So we want to look at how temperature changes through time to a certain degree. What we did on Tuesday in class was we looked at a steady state temperature system, so not a time-changing. So, and then this bottom one, you could look at it both ways. It actually doesn't say whether or not the slab starts stationary and then starts moving, or if the slab is always moving and it's a steady state system. So what are some more steady state systems that might be interesting? Or time varying in a cyclical way that would be interesting?
Like seasons?
Mm-hmm. Very common problem we have to solve.
Summer, fall, winter kind of thing.
So what might be an interesting question?
Looking at glaciers, how they melt in the summer. Don't melt in the winter.
Or diurnal circle, night and day, low and high.
Diurnal cycle or seasonal cycle, and what might we be interested in knowing about how that cycle affects, like what is it that what are some things that change temperature with seasonal or daily cycles that we might be interested in?
Like permafrost thaw.
Yeah.
Permafrost is a great one that's here. And whether or not, if you want to get into the thawing, phase change, but you can start with just, how warm is the ground? So that's another good one. Ground temperature over daily or seasonal cycle. What else?
Maybe sort of going on with that, how much insulation does like a bear need to hibernate in the winter?
So a building with a tin roof, how the temperature changes between night and day in the summer of southern Alabama.
Of southern Alabama, yes.
Let me tell you, it gets hot in the daytime.
Yeah, well that's great. That would actually be a variation on the bear. So the bear needs insulation here, but in Alabama you want a reflective coating, not an insulating coating. So that could be actually a similar type of problem. Yeah. Okay, so we've covered a little bit of some ideas for daily seasonal cycles or these kind of things. Is there any other you something from your, is there anything from your research that
A
indicates
comet.
the magma body?
Yeah.
Hmm?
A comet that gets close to the sun.
A comet that gets close to the sun. Like an ice comet that might melt? Anything else?
If you, so I guess if you have a lake in front of a glacier, and it's going into the lake is cooled to pretty cold temperatures, but any heat that goes into it, it kind of, like that goes into warming up and melting the glacier. So I guess, if you had a glacier that was covered in, a little bit of snow and had like a very high albedo and, not much of the sunlight is melting it, whereas water has a very, low albedo. What would, if the lake wasn't there and the valley just kept going down at the like rate it was, how much longer would the glacier be, to be the equivalent of having that lake? It's kind of a weirdly phrased problem. Maybe I could phrase it better.
I'm gonna put that for now under the more complicated problem because
Yeah.
it might involve phase change with
Yeah.
liquid. So glacier melting into lake. How much can the lake melt? And we could talk about some of the different issues that we might have to think about with that one. Yeah, that's a good one to get us started in the discussion. What else? Any other hard ones?
Maybe it's not as hard, but another just idea is if you had, say you had a solar sail in space at some radius from the sun, and you can tell it, you can see it's accelerating at some small amount, and if you knew the radius of the core of the sun, you could ask what's the heat production in the core of the sun.
And how much, so the heat that the solar sail is intercepting, is that? What you
Yeah,
mean?
because the heat energy would be transferred into kinetic energy, and you'd have to use the black body radiation, I think.
Well, we could add a related one that might be a little bit simpler. Is actually also would be, and I think Joshua, you just did this in my class last spring, and that's what is the surface heat flux hitting the top of the earth, or it's hitting the earth.
Surface.
Well, yeah, you could do
The
that
Earth's,
too.
yeah, the Earth's surface, you could look at it at different points in its journey, but we could get all the way down to, what are the watts per meter squared on the surface of the Earth. That's a good, that's one that, well, we'll think about this. I don't wanna give you guys a chance to kind of think through. Okay. So, let's do this. Team up with somebody. You guys have been sitting in the same place, so if you wanna move around, you can. And let's have one group of you, one team, think a little bit about or you could either pick one of these or think about the variations that each of them would have. Because all three of these are about taking something at one temperature and then seeing how it changes through time. This one you could also look at a little more broadly. So with this first one, our question is, how long does it take for the pizza to get to a certain temperature such that we consider it cooked? Right? This one, how long does it take for the cup of tea to reduce itself down to close to room temperature? Ice cube melting on the counter, you could make that one more complicated if you wanted to, with phase changes and all sorts of fun things. But that's a start. The cooling magma body within the crust, the one variation on this that makes it, I think, a little different, or could make it a little different than the others, is if you've got your magma body, we're just gonna make it, you could be interested in the temperature both outside, so the bedrock around it, as well as what's going on with the temperature inside, and then how all of that is changing through time until it would eventually solidify and become the same temperature as the surrounding country rock. Does that make sense? How that's different than the pizza? Because in the pizza, we're not as necessarily as interested in what happens to the air around the pizza. And there also might be, in this one, there's a source. You could think about subtleties with source versus not. So one group, I want one group to think about those. I want one group to think about the slabs and the movement, and then initially, and we'll probably get to more of these, and then one group to look at the ground temperature over a daily or seasonal cycle. And I will come around and kind of help you think about what the boundary conditions would need to be, what are some different assumptions you could make. You might have a choice. Do you make assumption A or assumption B, and how might that change the problem? Or approach a slightly different variation on the question. And so we'll just take about maybe 10 minutes to sort of focus the question, and then set up what you think are the best assumptions to make, and then we'll share among each other and then talk about what the different variations might be and what the next step would be. So who wants to do the first instantaneous cooling of something starting from an initial condition? Okay, you two. First one's raise your hand. Who wants to think about movement relatively, movement along with it?
Sounds interesting.
And you can vary, you don't have to stick with exactly what's written here. If you want to vary it to make it a little more interesting once you get into your routine, you can. So, Emily and...
You came up with it, right?
Yeah. Okay.
Okay, Emily and Lindsay. And then ground temperature.
Yeah.
So write out a little more what you feel like the most critical question or the most interesting question out of it would be. What does that mean in terms of your conservation of energy law? Which terms do you need? What are the assumptions you're going to make about steady state, advection, diffusion, sources? What's the geometry of your problem? Can you do it in a simple 1D geometry? Do you need spherically symmetric geometry?
It's like a spherical cow in a vacuum.
I left mine really big, like so many assumptions to do. Like really
So,
dense.
heat's in the oven.
So we should assume the easiest is how we get same insulin. Right.
So that has no chemical energy.
There's no chemical.
Hopefully.
Yeah.
So
Or seasonal.
assume steady state.
Um,
always when moving.
Yeah, so we
It wouldn't have viscous strain either.
ground.
Yeah, the cheese wouldn't
We have
do anything.
air.
Do we want it to be
Or the air.
similar
I guess
density
there's
or
the air,
same
there's the
density, or
sun.
density, the bottom has more. is more
So,
I'd say
There's
it's
the
different.
so
So
well
the
So
is the heat
the body, the initial
the air and the
temperature must be
sun.
0,
So
0,
there's
like in
heat
the beginning.
or
The top of pizza.
Oh, okay, yeah.
The bottom of pizza.
So we're assuming 2D
So-
aspects.
I guess so. We could do it in 1D, but
Some other
Oh, yeah,
assumptions
1D
we can
aspects.
make.
yeah, it's probably
It's
in
the
fact
same.
probably assume 1D.
Yeah. So we have 1D.
At some point in the ground, there's
There's some constant.
like
Does it
there's
matter
flux
how-
upward.
I assume heat would remain
I
constant.
mean, okay, say
Like the temperature.
Of the
So the-
air, of the
So
oven,
temperature's
yeah.
gonna vary by
What are we looking
our
for first of all?
dimension
I guess
by
what the
let's just
question are
call
we
it
asking?
X.
the question I asked on there is, does the movement change the temperature
There's
gradient
also-
between the two?
I mean, if
Because
we
like
wanna make
I
it more
wanted the
complicated,
T1
any
to be
sort of
like
like
outside
rain
of
comes
here
down
touching it and
is
T2
in the
there,
soil,
so
but
there'd
let's
be
just say that
temperature gradient through
Assume
those.
that
Yeah.
pizza is
Oh,
moving.
so like our original
formation
problem,
of
now
the
there's
pizza.
a
Right.
split and half.
Yeah.
Yeah, or you
When
could
we
just
work
say
together.
the T at this boundary is T2
I guess it's-
and the T is
if-
Okay.
Is the heat
So there's gonna be a gradient, right?
Move?
Well,
Yeah.
I
We're in the
want to
attic.
know
Yeah,
Desert.
and there is no
Between
reflection
the
like
parts,
towards the
whether-
Affecting-
sides of the oven,
Yeah.
so it just
Yeah.
So-
It's just coming down.
The attic
Yeah.
has the
So does that
least
count as
But if there's
advection?
friction,
anywhere on there.
yeah.
Yeah, or we have to assume
It's
friction.
been like
Hmm.
years since they've had
That's just
I
that's
mean,
what I'm
recorded
Well, we don't have to because
measurable
there's no
kind
friction, then of course
confused
it's
about.
precipitation.
Okay.
because then we'd have to have like the
Telescopes there.
velocity of the heat
So
of
Anyway,
hot air.
we have
So there'd have to be like a fan or something that was producing.
just
so
constant
there is
speed.
convection from the oven,
right.
right?
I'm just gonna call
Well,
it QE, or do you wanna?
Should be GP or
well, it should be 0, right? Because we don't have the velocity of.
Well, that's that's what I'm saying. Like if there was advection,
Oh,
we'd have
if-
to have like a fan or
if-
something in the oven
So your
pushing the
diffusion-
heat,
yeah, your
like
diffusion is
forcing
gonna
airflow.
But if we are, assume that it just
That's-
has
that's
a good
gradient,
question.
If you have a
Calculate.
velocity of airflow,
Yeah.
it shouldn't
Not-
affect
yeah.
that
No.
should part of the problem.
Like,
Since
okay,
we're not
which
using
if
a
heat
number.
is moving
Slabs,
from the top to the
So
bottom,
these-
bottom,
there would have to be
Greater
something
than
pushing it that way.
Yeah.
How about like the
Well,
previous example from the
Yeah.
2 days ago, like
temperature
when the heat is
is
transferring from the
Yeah.
outside to
And so
the
now the
to the
movement
wall,
is
like
just-
Yeah.
the heat is
Um,
moving,
We're
but
going, or do we want to
we assume that
We've
it is
assumed
0,
that we're
right?
in
Sure.
the attic
Well,
of
we'll
the
just
desert,
say
because
we can
there's
put a
almost no
little
precipitation
Because
the wall
there,
is
and
moving,
that
but the
would
heat can
complicate
move.
things.
Yeah.
Okay.
But this is
Done.
air. That's interesting.
Yeah, so there's
I think
some
we
sort
should-
of.
But the so the
some
if
sort of
we
temperature
ignore
entering
that,
the
then
top
it would
of
just
the
be
ground.
like
it's in a
the
vacuum.
oven
The
is this
air
hot
and
and
the
it's
sun's
staying
in
that
the
hot and
air.
not changing.
Yes, the air
Yeah.
is not
also
moving.
a
So like in a
constant flux
vacuum.
coming up from the air. So there's gonna be
Huh.
so there's gonna be a
Well, I mean that's kind
temperature
of.
profile in the vertical direction.
This-
I realize ovens are not vacuums, but
Yeah,
Do we
but
want
that's
to
kind
use,
of.
like,
So
Do we
we'll
wanna
just
assume that there's
heat does
flux
not
is
equal zero.
changing,
Yeah,
or
that's-
is the
that's a
temperature
good
For
point.
our,
from
to
the
make
top?
this an actual problem.
I said it was
Good
implement
question.
here so that you could
I feel
ignore
like temperature
the
mean-
would make it less.
Boundary
horizontal.
Like
Well-
you said, it's the temperature is changing.
Okay, yeah,
So it would just be.
no change in horizontal direction.
Interesting. Yeah, because there's gonna
Well, I don't know because
Like,
Well, let's
there's
give it a coordinate system,
It's
so.
a good start, and that's a
There's
good question to come up with.
friction.
but the
Then
flux
there
is
would
gonna
be
is
a shear
gonna
stress
change.
horizontal
I mean,
How are you
there is
gonna
gonna be a
scale?
constant like we can assume.
And so the
what
final,
temperature
we
Okay.
don't know how long
Oh,
it's
no,
gonna
There's gonna
take.
be a lag.
You made a point. So
That's a
I
good
think-
question. Let's.
yeah, so we're just.
I think we
trying
can.
to
There's a
come up with
Does
some
it matter?
at some point
Yeah.
down,
Like
So what's
how long?
your-
I
do you
mean,
narrow
as long as
down
it
or
reaches
adjust
Point
the
D.
question?
Well, like,
the
where
tea
the
oven.
temperature's the same.
We wanna
No, we're still
know
looking at
when
Like
the
Okay,
pizza
so
gets
it's
as hot as the
been-
oven.
yeah.
Okay.
moving. It's in a steady state.
Okay.
Forever.
Yeah, forever. So
Ever and ever.
initially it had its a nice just gradient
Yeah.
depending on this is the temperature outside here, this is the
So,
temperature
I'll
outside
call
here.
it
Yeah.
Kind of like yesterday
Um,
or Tuesday especially. Now it's been moving, and so yeah, we're still wondering
So-
does the movement change the gradient
But-
within each half of the block?
Sunlight, the
Um,
actual heat flux coming in
yeah.
from
I think it only
sunlight
does if
sometimes
it's-
lags.
Yeah, if there's no friction, there's nothing. Yeah.
Density
That's
of
not
sound.
gonna
change.
But make sure that you see,
Okay.
so can you, when you're
Hits the
right.
ground. But then
What
again,
is C
but
of
look at
if
the
feeling?
sunlight
equation.
hits the
Let me
ground,
see
the
that.
ground
Okay.
Colin
Right
does?
here.
Yeah, the one
radiate
right
air
So
off the
I
ground.
want you to prove.
Sort
It's just a
of.
material
Yeah,
property.
Yeah,
Is
material
prove to me
property.
why that
Worry
velocity
about
of that slab doesn't matter.
Specific heat.
If
It
there's
doesn't change.
friction,
Okay.
Let's
if
see.
there's no
If
friction.
there's no friction,
Yeah.
if your instinct is right, but I want
Good.
you to show me how that, I mean, you don't have to solve the whole thing, but just
I know
what
that
does that
reality.
mean
I
in
think
terms
that's
of
as
the
far as it-
equation?
Yeah.
The hottest time of day
Absolutely, we can.
corresponds to
so-
the peak.
Where does friction go in this?
Yeah, in
It
the
lags
ground.
about 4 hours.
So friction would be
But-
one
One
of
of
these,
those.
cause this is kind of like an internal viscous friction.
Yeah, and
This is
'cause the
a
heat-
radiative
'cause it's
source, so
only,
these are all
um,
sources,
heat diffusion.
and so you
That's the
could
only thing we
have.
So if those are if friction 0, these are 0.
and going.
Should we assume that the
through-
Friction
pizza
so,
is
yeah.
super
Those
thin?
are both 0. And you
So then
could
we-
put
I don't know.
friction in basically as a
See, I think
line.
heat
Well, as long as we
diffusion is based
have-
off
along
temperature.
that slab boundary.
Super thick.
But yeah, if you don't have any
Actually,
friction, then those are all 0. So what
we
else
don't
is
have to
0?
worry about
I
this.
actually think that question is.
Well, we're always gonna have to worry about that because that's
Oh, otherwise it will
the
be.
heat of the oven.
We're assuming
Like
that
that's.
Ah, yeah, yeah, yeah.
Right, so, yeah, derivatives in the horizontal direction would be 0.
Yeah. Because this is change in temperature over
And
air or like
What is,
distance.
what
It would be like
changes
from.
when you have a velocity
Mm.
versus no
Oh.
velocity of that
basically the
slab?
same thing. It's just
Momentum.
cosine or something that's constant.
Where is that in this
So it
equation?
doesn't.
Okay. Well, so it's
Like, there
it's
has
gonna
to be-
It's gonna be a.
Oh, you're
I mean,
right.
there's seasons.
Yes.
Well, maybe.
So like we're worried about
So,
day to day
velocity
and
is there, and
seasons.
what are the
Um,
phase in this
Very white.
equation? Can
So
you write that
I guess
out?
first we could make like a
Right, what else?
Just this
season,
term
a daily
out?
equation, and then a season
Because
equation.
it's just like
It's
through-
right, the-
Yeah, it's
Like
The
from one
ground-
surface to another surface,
the
not
ground
like
is
through
gonna
a thick
radiate.
thing.
Or you, yeah.
Add
The
over
heat-
them. So
the-
what are
the
the
sun's
three
heat that
terms
hits
there?
it
And
gets
which
absorbed.
ones
I
do you
think
just
yeah,
call
it should have some
0?
thickness. Otherwise, it will be linear. Like if this
you'll
one
know
is
better
Which
about
ones end
the
up
albedo
being
would
zero
be.
and not
crossed
velocity?
out.
But
I'm worried about that.
yeah, so like
Right
whatever
on.
heat
The
gets
heat
absorbed
just touching
is
it
just
and
gonna,
that's it?
Like
Yeah.
warm up the air
Oh, you
because
guys
air is
don't
gonna
know.
compress. So air is
So
You know these are
looking at the one we did
more constant.
on
I think, right at the
Tuesday,
ground, but the
we
air
were
is gonna
looking
warm
at
up and
the
cool
temperature
down.
change and a thickness of something.
And so
But where this is
flux,
just the difference
and so air
between-
temperature is
like-
I think a
We're having
loose
trouble figuring out
function of
So
Should we
the-
assume
if
that
it's through the like if
Yeah.
through this is our distance that we're
For
trying
air
to heat,
temperatures,
or if
a
it's
loose
just
function of heat
like
flux
over
in the
the
sun,
surface between
But we
the
have
hot and the cold.
what's
like,
So this is
with
the
a lot of
pizza and
weather
our
Yeah.
version.
added in.
Well, let's
Okay,
call
so you've
it
got some assumptions, no
quality.
chemical energy, no
Desert.
viscous strain. Those are good. Pizza starts out at 0 everywhere.
Okay, well, because then.
So what's your constant
Yeah.
T hot?
then,
What
I mean, we
assumption are
could
you making there?
set up a model.
Especially
The
if
oven
it's
stays
going
at the
to
same
something
temperature.
I'm like,
So you're gonna assume that all of the surroundings on every
So-
side stay at the same temperature.
Yes.
I would
Okay, so the
call-
top
well,
and
actually,
bottom
maybe one,
Yeah,
but
Are
would-
both
like
at
starting
temperature
Oh, yeah,
equals
yeah.
T hot.
Yeah.
'Cause the-
that's
It's like
and-
there's air temperature, so.
Yeah,
there's-
so,
as I see it, there's
I don't know
um,
if you're either direction. not
air.
so if you go back here,
one.
in your case, T cold and T hot are equal.
Upwards, 3 would go outwards.
I mean, if we just take the same
is
drawing.
constant.
Um,
Mhm.
what's in the middle
I'm not sure how these
starts at
It's
0.
like
Mm-hmm.
you're
Yeah.
Science.
And so
Yeah,
you
yeah,
actually
we're
have
doing it.
some
Yeah.
similarities
So
with the
this
approach here. You're making some
This is
similar
related, so
assumptions.
T1
Yeah.
is related did put the legs
but
behind
just
TA.
think through what does it
When you're
mean.
doing it with your left hand too, it has to
Here
be
we
right
assume
hand.
steady
Alright, the
state.
temperature at the surface.
Yeah, T1
That
is
was coming out.
And so we got rid
Air
of
would lag after
this
surface.
term.
Yeah.
Here you can't get rid of
Yeah.
steady state.
Oh,
Yeah.
So what you got there.
But
I mean, they're just like a.
So
yeah, that's true.
then the next question would be what, so here you have one term
Or
and
do we-
here you have several
Or do we want to
terms.
simplify it and say,
Because-
let's say that
That's right.
Yeah, if you were looking at all three dimensions, you would have lots of terms.
Mhm.
So basically from your geometry start
we
to
could assume
figure
there was
out,
a moon.
well, can we simplify the geometry enough that we can get rid of a bunch of these terms? Um, and then
No, I'm not.
I draw a little,
Okay,
I mean, you
well,
sort of
in that
half of a
case,
diagram, but I would draw a more
straight
specific
up
diagram
you
based on
plug
what you
in.
assume about the geometry, what your specific
the
boundary
moon
conditions
has
are,
a
which are the
different
teapots,
Yeah,
inside
what
it.
your
2 and
initial
3
condition
are
is, and that's
zero
at t
because
equals
we're
0.
Yeah.
This is what
Yeah.
it looks like.
Interesting.
And then just
And
do, start
Every
doing what
terrestrial
we
body
did
has the really long
yesterday,
moon.
just thinking
Oh,
about which
right.
terms we can get rid of. What do we know? What do we not know yet?
Or no,
And
Thorium's
do we need to
green.
make more assumptions?
So we
That's-
can't
But
do
yeah,
that.
you guys are on the right track.
Although changes.
changes-
It's a little bit different than yesterday because you have an initial condition.
It's not
It's a
changing
time
the
changing
temperature
If
this
on
way.
the moon,
Mhm.
because
Because
maybe
the
we should
gradient's
come back
only
to
up and down.
this, or this
What do we
problem
do?
we worry about.
So I think we should kind of,
So,
this is gonna sound
If
weird,
it's
but
steady
like
state, we
assume an
wouldn't hold
infinite
things in
pizza,
forever, so
Oh,
the
yeah.
whole
Like infinite wide.
constant
and like
density
we only, we wanna know when
Yeah.
like the exact center of it is heated all the way through.
Ah.
Cause the worst thing is having a frozen center of a
Like
pizza.
intuitively it seems
So
weird.
then we don't have to,
I could see
Well,
it.
yeah, just because we're used to it being
there's still gonna be
initialized,
some
like,
point
not
it's
moving.
constant.
Wait, maybe that doesn't make any
The
sense.
only,
Initial
some like
Yeah.
depth to where
Base
the
and
temperature I
physics
think
are
is
good.
constant,
But
not
here, if we
affected by
just
these
assume it's been doing
cycles.
So if it's
forever,
constant in X1 and
It's
2.
probably a lot.
then
Yeah.
we're not
further
getting any
down.
changes in the X two direction.
But there'd be
So
some
that's
point
why
where
it's
if you go
changing.
down, I think that it wouldn't be
But
affected
then
by
the velocity in
you know, the
one is
day-night
zero,
cycles.
So we're just gonna end
Eventually,
up with that whole
you get so
term
deep
being
that-
zero.
Which that's what we're trying to prove.
Yeah,
Oh,
which
this
I
if
think
there's
is
no
the,
friction.
Yeah.
Giving it a constant
depth.
density.
we can assume there's a
So-
depth
Yeah.
like that. In fact, you might
Yeah,
even be able to solve for
Yeah,
that
velocity
depth.
here. Alright, so
Um,
we took out all these terms this time
So what
again.
is all of this stuff?
So,
I ran out of space for notes, so I had to go to
Okay,
different
take
things.
about 1 to 2 more minutes. Kind of get to a point that you're gonna explain the beginnings of the problem to the whole group, and then we'll talk on from there.
okay, so the
So we're looking for
Initially it's
So-
DT and time, when there's no friction. So this is what we're trying to
technically we're setting this to 0.
Yeah.
if we're
Should
saying
be
that
zero.
we're trying to prove that this is 0. So
The
when
equation that
this
we're
has to
gonna
equal
solve
0.
is
Well, that would be the change in the two direction, right? So
Why would this be in the two direction?
I'm just saying, it's just.
we're assuming that our
Actually, no, that's not.
conductivity is
that's not-
constant in all directions.
I'm not sure what to do with this.
Well, we would sum that one too, right?
So we can get this.
yeah.
Oh yeah, so,
So-
wouldn't that be like 1,
well is
Mhm.
1, 1, 1, 1, 1, 2, 2, 1, 1, 3, 3, 2, 2.
yeah. Well, I mean, I was trying to think of this a little bit easier
Two,
way.
two.
The,
2, 2, 3, 3,
just
I'm trying
we
to
have
include all
some.
of them. 3, 3, 1.
Yeah, it should be linear, isn't it? Like
Yeah.
if we assume that
Yeah, it'll be equal,
yeah.
in which relates
like
to
it'll
the
be
surface
equal this
temperature.
direction
We
and
know
this
that the
direction.
temperature
Mm-hmm.
is not changing, and
Oh, that's why I didn't want to care about the edges, because
X.
there would also be heating
Yeah.
from this way, so we're gonna
2 or
ignore that.
3.
One.
Because I
and
feel like that would be
then-
confusing.
then we're just looking at
Like so what
Two
I was,
is
I
gonna
was thinking
be-
is if the pizza is super wide, like 10 meters square, and
Mhm.
it's super thin, so we can ignore the thickness.
so
Like either one of these must be the thickness, right?
But if you ignore the thickness, then
So we
there's nothing that's cold.
Bottom.
so we end up with this. We can integrate and we get the constants.
Yeah, it's not going to be
And
constant.
we can get the T.
Okay, last.
It's kind of linear.
Couple
I think.
thoughts.
If we integrate that.
Yes, we need to solve.
If we're saying they're going to
Sorry.
this direction,
Okay.
Well, this
You
isn't
guys
changing.
go first.
Yay.
The simple, well, hopefully you thought about that, the
We were
first
trying
part
to
that
do
I.
the friction part. but
Okay, yeah, that's where
we
you get a
did
little
do
more
that.
complicated.
Yeah. Well,
Yeah,
we were
first start
doing
with
no
that.
friction.
Yeah, do
We
the
got-
no friction version
We got
first.
this part, but we're working on this term. Maybe you can help us.
Okay, yes, I'm always here to help. So explain your question and then the first version, which is the no friction version, and the second version.
Okay. We have our slabs. And the surface is at T1, T2. There's a velocity going in this direction. Using a certain thickness. And we said these infinite slabs. Oh, and we said this one has a density 1, density 2. And then some of the assumptions we decided
With our coordinate system.
oh yeah. We did 1, 2, and 3.
And where's your origin?
We would put it like on
Okay.
top of there. If since they're infinite, I mean just wherever on top of
Yeah.
the top slab.
Well, it could be on top, in the middle, or the bottom, so that's.
It's just constant.
Assumptions. Okay. V has always been V naught.
So steady state.
So steady
It's
state.
been moving forever.
Been
Everything's
moving forever, yes.
nice.
The density of 2 is greater than the density of 1. So there's no. That's steady too, since row 2 is on the
Oh,
bottom.
so we don't get into convection and all sorts of crazy thermal densities.
Oh, the slabs have also always been there. In the same.
Okay, we got it. Steady state. You
Yeah.
can just say steady state if
Okay.
you wanna.
Steady state. Oh.
Okay.
No, I don't have room to write anything else.
There's a
What
little
about the
room
specific
that-
heat and the conductivity?
Can we just say those are constant?
Yeah.
Okay, so. And. Constant.
Okay.
Oh. And these are constant.
Okay.
So the first case we looked at was if there's no friction between the two slabs. And let's see.
So as you guys can all see in this long equation that we do not necessarily have room to write on the iPad. So you can take out the last two terms because that would be,
It's just
thank you.
extras. I put more space on that today because I felt like
How
it was more
exciting.
scribbled.
Because that would be where the frictional component would lie. So then we looked at I guess it's the middle component there, the rho CV velocity times change in t over change in x, and so no, we don't have to write that. So
Well, that term ended up looking like
you have two k's, so you're summing over them. So you're doing rho c u1 dt dx1, and then u2 dt x2 plus u3 dt x3. Okay, so we know that the temperature is not, since we assumed in infinite directions, temperature is not changing in the 2 or 3 direction. That's not where the gradient is. And in the 1 direction, the velocity, there is no velocity, so that's why that term also goes to 0. So all three of those go to 0.
Right.
This is assuming no friction still, so we're hoping to get everything to 0.
Right, so do you guys see this? That even though the plate is moving, and this would be true if it were a fluid too, even if it wasn't the whole thing moving the block, even if you had some pressure-driven profile of velocity like you guys did from the last problem set, any horizontal movement ends up being 0 because the whole term is 0. So even for U2 and U3, U2 is non-zero, but the temperature gradient is 0 in that direction. And so it doesn't matter how complicated U2 is, or U3 if there were U3. It doesn't matter how complicated they are, it's still not going to affect the temperature of the system. Because all you're doing is moving stuff at the same temperature from one location to another at the same temperature. So you're not going to change that temperature profile. And on this one, U1 is 0, even though there's a temperature gradient in that direction. So that's good. I mean, that's one point that I think is really easy in a more complicated problem to be like, oh my gosh, how is this? There's all this movement of fluid around or something moving around. It is a very good thing to recognize that it's the movement within the direction where there is a temperature gradient that matters. If there's no temperature gradient in that direction, it doesn't matter. So that's good. Okay, so now what did you try to do with friction? What was the assumption you made with friction? We can, I don't want to read you the whole thing, but we can, so most of your assumptions are the same, but what's different now?
Now we're assuming
there's some kind of shear stress
Yeah.
at that boundary.
you can make
I
your
think you
eraser
can
bigger
make
if
it
you
bigger,
can.
yeah. Okay, so we still have steady state.
Okay.
We still have steady state. We still have the given temperature profiles. We still have the steady velocity. So what's changing in this equation now?
This is not 0 anymore.
So these, and I do want to just emphasize
The
again,
last.
the last two that I listed here, one is kind of the magic radio, the chemical emissivity, because to me all chemistry is magic. I was so bad at chemistry. I don't have a huge respect for chemists because it looks like all magic to me. And then the sigma times the strain rate, that's the viscous strain heating. So this is for a fluid, so if you have a strain rate, which is something that you really typically only get with a fluid, you would have a strain heating there, a viscous strain heating. But these are both any source mechanism. So if you have a source the car engine in the next problem that we might talk about is a source. And so you can make those sources whatever you want. You can just call it a big S and say that there's a source, and it might be a point source, it might be a line source.
So that's
It-
where our friction would go in that.
Yeah,
right
so you don't have to stick it into the specific model that's right here. You can just say we have a line source or a plane source, and it's emitting energy at a certain rate. So what did you? How far did you get on that? Because that's what it seems like. That's what you started. You
Oh,
would
we
put it
had
into
just
this. You lumped it
started.
in there. So what would your final equation look like once you get rid of as many terms as you can and you have your source
Oh, we
term in
really
there?
did not get into that. This is not from today.
Right, but you already did all the work in the last problem. There's only one change between what you did a few seconds
So
ago
this-
and today.
This is what we're looking at there.
I mean, and right now. So you got rid of this whole
Yeah.
term, right? You got rid of that whole term. What does
How do we
that
get rid of
term
this
look
whole
like
term?
given your geometry? It's in steady state.
Did you solve that?
Did you
Oh
guys
yeah,
see?
that's
So-
right. That's right. We did say that.
Yeah, so you got rid of that term because it was in steady state. You got rid of
So
that
I-
term. You got rid of all of those. So all you had
So
left
I
was
assumed
this.
So now I'm curious about what this question is asking then.
Super
So we say that
solving that.
did the movement
So if it is
affect the
super
temperature
thin,
gradient? Do we need to know the initial
either one
temperature
of these
gradient
because-
then?
It's been
So
like
it's
that
all-
forever. What
But
is the
this-
solution to
and
that
then
temperature
I
gradient with no
left
friction?
This, then I integrate again
We
I'm
did
not
it on
sure.
Tuesday.
And T,
Well, we have
it's
different
constant.
densities,
It
so
means
does
when
that
you
change?
put
Does that
really
does that
How
have
does-
picture?
and
How do
So it's
how
still
does-
from
linear?
the oven just
How would the
suddenly, like,
density come in and
boom,
change
it's-
that?
Because it's put in.
I'm honestly not
Yeah.
sure.
So it's like instantly changing.
I guess it would still.
That's I don't know. It's kind of crazy.
Well, yesterday or on Tuesday we did one version where it was all the uniform material and it was a straight line.
Yeah.
Right?
Yeah.
And then what did we do? I said it was two materials. And
Oh, that's
what
right.
did it
If
look
you
like?
increase the density, then it, or did you? Was it the density you increased when you were talking about two materials? I can't remember that. But
What are the-
it changed the velocity throughout.
The
Yeah,
velocity.
right?
The temperature.
Temperature, not velocity. Just kidding.
So the material properties involved are density, conductivity, and specific heat. We often lump all of those together and call it the diffusivity, which is the kappa. So it doesn't actually matter whether it's the density that you change or the specific heat or the any
Okay.
change in these two materials,
Would you
and you would be changing its thermal properties. And how did that change our solution on Tuesday?
They made the lines go from vertical to they had a slope to them.
Can you draw that? It starts out one straight linear line from T1 to T2.
Okay. It starts out like this.
Actually,
I'm not worried about
Still
it.
on your race?
Yeah.
we can solve this.
Okay.
If the pizza is thick, it means we
Well,
input
so-
the
Oh, it was a
integrate.
slope. It
So-
started out a slope.
Oh
If we
yeah.
express temperature in a horizontal way,
Oh,
so
okay.
we sort of-
It's basically
Yeah. So we
This
started
is
off
from
with a
Okay.
like a nice little slope
So it was like
because it was just a linear gradient.
is it going that way or that way?
It depends on what which one's greater. So
So
just you could just do it in
Why
line.
don't you just draw?
So it should be 2 times faster.
I don't. It
Yeah.
doesn't. It probably doesn't matter. I guess. I guess
But
that's our origin though.
Steady
Ah,
condition.
well, that's
I think they-
that's as straight as I'm getting.
They assume that this is 0
That's fine.
on two
So we have
sides.
T1
Yeah,
at the top
but-
there,
for that.
T2
But right
here,
now we are
and it's a straight line between if they have the same properties. So
Mhm.
what was different if they have different properties?
So, at that boundary,
Yeah, we can solve
one
that.
would change.
Right. And which way it changes depends on which one ends up being
Yeah,
more conductive or non-conductive on the whole. So
because that conductivity includes the thing like density,
density
all
is in
physical
there.
properties.
This
Yeah.
is a solid. If you were to have it be a fluid, and you had a density that depended on temperature or some other stuff, then yeah, it would get more complicated with the densities changing. That's how you generate convection cycles and stuff.
So given that we know it would look something like this, we're just seeing if that changes. If that has changed because of the movement.
Right, in which case it hasn't, right? Whether, no matter which piecewise linear version you have, none of that is going to change with the velocity of your slab.
Even with friction?
So
with
with
friction,
friction,
adds,
conceptually what should be happening if we add friction along that whole line right in the middle?
I mean, you're heating it.
You're heating it up. And you're causing...
you're changing the boundaries of each slab to different temperature conditions.
Right, so we're taking this point
how long it takes.
and we're adding a flux of
Time,
heat in
yes.
at that point.
If that's
So it's going to try, it's
Shall
trying
we
its darndest
change
to
it?
warm that point up. And where does that heat go?
Into the slab.
Into the slab. This could get, I mean, so if we actually do keep, this is where some of these
I
problems
guess we need to
can
know what
get
T1 and
tricky.
T2 are also, though, because if, say, the frictional heat is colder than T2, then it's not going to move towards
Right.
T. It's
So-
not as hot as T2, then the heat's mostly going to affect one slab and not the other. So we need to know if T1.
But if this has been going on forever and we've had friction there generating heat forever,
Does it
What
involve
is it?
with changing energy, like from heat to, I don't know, sound or that kind of thing?
you're already bringing in Maxwell's equations
I know.
in your microwave question.
Oh, yes.
Now you want to bring in the wave equation from sound.
I mean, that's true. Heat energy can,
It's a good
energy
question.
can turn into other types
It can
of
turn
energy.
into other things. But if we're constantly adding heat to the system, but we're saying it's steady state, we have to pull that heat out somewhere in order to balance the heat we're putting into the
That's
system.
The movement.
And so to get heat in and out of a system,
Faster.
it's not just the temperature, because the temperature just tells us what the temperature is, the amount of energy that is there. What tells us how much energy we can move?
Can I do?
Yeah, the
No,
velocity.
not velocity. No.
Changing it.
We want to move heat, not mass. We're just moving heat around. How do we do that? You guys have it as one of your boundary conditions.
The heat flux.
The flux. So the flux of heat is moving it. The temperature means it. So you can have two types of boundary conditions: the temperature itself or the flux of heat across that boundary. In this one, we're keeping the temperature steady, but if we wanted to transfer more heat, if we wanted to transfer heat out faster, given the same temperature at the boundary, what would we change? How do you increase the heat flux?
Reducing the volume, or increasing the energy.
What's the equation for heat flux?
You increase the conductivity.
You could increase the conductivity or
Increase the gradient.
increase the gradient, right? dt dx. And times the conductivity gives us the heat flux. So if we're generating heat inside as a source, we would it would have to eventually reach some kind of a gradient that would balance getting that heat out at the top and the bottom. If we were in steady state. My instinct of what this would look like, this may or may not be right, because it can get tricky on you if you're not paying attention. So we have T1 here. Say we have T2 here. It's a little bit warmer. We're generating heat all the way along here. My So there's two, and I can't do this problem in my head. One option is, and this might be the right one, it's going to look like this, where a certain amount of flux is going out the top, a certain amount of flux is going out the bottom. I'm actually pretty sure this should be the solution. In this point, T of our source depends on how big of a friction coefficient we have, how much energy we're so we don't know this, but we could find it if we knew our the Q of the source, so the heat we're generating at that point along that line. And this, the goal of, the reason that this has to be at a certain temperature is because we have to create a, so we have some conductivity times dt dx. That is what equals the Q bottom, how much we're getting out the bottom. And the same thing up here, Q top equals another K dt dx. But this dt dx is this slope, this dt dx is this slope. And they'll figure out their slope that they need such that the sum of these two equals our source in the middle. Does that make sense?
Mm-hmm. The answer to our question is yes, it will affect the temperature gradient then.
The friction will,
Yeah.
Annie and Joshua, does that make sense to you guys? I think that if you just turned on the friction, then it would take some time and you would have a curved profile. But I think that once it reaches the steady state, it does eventually become linear there. So,
That makes sense.
got it?
Mm-hmm.
Okay. That's a good transition to you guys because you have a heat flux boundary condition too.
Take the lead.
If you
Oh,
wanna.
no, cancel this button. There we go.
Well, in looking at, we had a problem of you have maybe I'll make it bigger. But you have some sort of ground. Sorry. You have some. Okay, so there's a ground. There's heat coming in. This is like the ground. How much does the ground? The question is, what's the temperature of the ground by X going down into the ground over seasonal and daily changes? And as we were looking at this and thinking about the air versus ground temperature and stuff, at first we decided to go with a desert and assume that there's basically no rainfall, because that would add a transport term. There'd be another layer of complexity. And then as we were doing that, and so we still had the air temperature and the ground temperature. And so then we decided that the thing that we could actually solve easiest in the amount of time we had would be if there was no air, and so we decided to take the moon. And so there's some. So thinking about the moon, it has a daily cycle of 28 days. But still, that's going to cause a temperature, like the ground is going to be warm and then it's going to be cold at times. And so, but there's going to be some depth, we'll call this D, where at that depth, it's going to stay a constant temperature. I'm going to call this T naught. There's Josh pointed out that there's radioactive material even in the moon. So there's some heat there. That there will be a point where the daily cycles on the moon don't affect the temperature, and you have a constant temperature there
At some depth.
At some depth. And so we were starting to be curious, like, what is that depth?
What is that depth? Yeah.
And so to get at this, we realized that our Q in would be where did I put it? Oh yeah. So there's going to be our Q. This is the heat hitting. And maybe this should be like heat per area,
per
but it's
unit
going to
area.
be per unit area. But it's going to be some sort of sinusoidal function. So we're going to say there's a Q naught, which is if it's pointing directly at the sun, that's going to be the total heat in. And so that we're going to have some function of the heat coming in, and then remember the equation that.
And what's A there? Just kind of to.
Oh, sorry. A is a time constant. I'm gonna set it to be 28 days. That A times 28 days is 2 pi.
Okay. So,
So-
your A accommodates the 2 pi and your frequency in terms of
Yeah.
days.
Yeah.
Because you need to get an angle out of that somehow, right? So
Oh.
you need to have
Well.
cosine of some radian. So you have to get rid of the time and turn it into a radian.
Yeah.
Yeah.
Yeah. It just A is there to make it so that when t goes from up to 28, then it's equal to 2 pi. I could probably work out.
No,
Just when I
that's
was-
fine. I just want to make
Yeah.
sure that everybody here knows. Like, the more standard way of saying that would be to explicitly say 2 pi omega t or something, where omega is a 28-day cycle. So
Okay.
you would make it obvious that you're thinking about it in a cyclical sense. But you've lumped that all into A. So I just want to make sure that everybody else knows that that this is like a 2 pi omega term is in that A.
Yeah, and then I was.
So, can we just pause for a
Yeah.
second? Because you haven't finished telling us all of your assumptions, or really just making it clear. So we have a bottom assumption at some depth where we have a steady temperature T0. We have a top assumption that's your seasonal or your cyclical heat flux in. Are you assuming one dimension and that it's infinite in the two other directions?
Yes.
Yes.
We're also
Okay.
assuming constant density, constant specific heat, and constant conductivity.
Okay, great. So it's a
And that they're
slab. With that, we
isotropic.
can kind of simplify it down to just what's happening in the x direction.
Yeah, I drew a slab. I mean, I drew like a block because I like to think about it as a block. But
That's
yeah,
fine.
there's only
No, that's fine.
one direction, and we'll call it x. And so specific heat, and so we can relate the energy coming in as by is that so we know our Q, so we know our E, so then solving this out. What did I say?
What's the other term? What does it equal? dt dt. What's on the other side of? We've gotten rid of, you don't have any velocities, right? So we gotten rid of the advection term.
Yeah, what did where did I say that? Oh, yeah. We also, sorry, that's an equation that we know, but then we can solve. We can solve this here. So that's well, I think we actually end up not needing.
So I'm not sure what you're doing there. That's your boundary condition. The Q
Yeah.
is only on the boundary. I don't even know yet what equation you're solving. Before you can get into putting boundary conditions into the equation, you have to finish finalizing what the equation it is you're solving.
I had.
From this, what do you have? What's
oh,
left?
Well, sorry, I was looking. I
You're
found
jumping
an
like
equation
5
in
steps
my,
ahead.
in my notes. Yeah, so we're gonna. Well, I guess I can solve or show what we end up needing to solve. I was gonna. So yeah, we have.
So what's
Alright, so we're just supposed to be partially split. And then we don't. So in this one, we don't have advection or heat production or
Strain heating.
yes, strain heating.
and then given your geometry, what can you do with that last non-zero term?
Yeah. So well, I guess I'll just write it out, but. So we know that, well, first of all, K is going to be constant, and
Okay.
IJ is going to be constant in any one. We're also, oops, that's
And that's dx, yeah.
dxj. Yeah, and it's also, we're only interested in one of the x directions, and so when you sum up xi and ki, you only get x in the direction we're looking at, and when you sum up kj and xj, you only get partial of x in the direction we're looking at, and so this is equal to k. Actually, it would be k squared, wouldn't it?
Mm-mm.
No?
Why would it be k squared?
If you sum both of them up, wouldn't they both have
What are the both?
the summing both the part kx, ki, xi, and the kj, xj.
How many of those are non-zero?
Just one combination, right? It's non-zero since we're only going in one direction.
Yeah, but
So you're just
wouldn't
gonna have
they,
one
wouldn't they,
term.
you'd end up doing two sums.
Could just be. You have the ki1, the other ones go to 0. Then you have a summation on the outside, where only one of them doesn't go to 0.
Oh, I see.
So it's only
Okay.
non-zero when both I and j are 1.
Yeah, so yeah, you just gave us one x direction, so just partial respect to x.
Yeah. Okay.
Yeah. So now from the so we have sort of relationship, which is going to be important. We can say something.
So I think I'm just gonna jump in because I want to get to the other problem and make a few comments, because this is great. You're going in the right direction now. That and this is the equation that we have to solve. So we have the partial of T temperature with respect to T, and the second derivative with respect to X. So it is a pretty standard partial differential equation. A lot of these, if you guys dig back into your memory about ODEs and PDEs, there are various standard methods for solving them. They're not all necessarily easy to just pull off the top of your head if you haven't done them before. But you've simplified the equation down to a version that we presume it looks like it's solvable. We have T, a fixed T on one side. We have a flux T, so we've given it and you could, so this is one thing, so you've kept this as Q, but how else, you might end up needing to rewrite your big Q and your Q naught in terms of the conductivity and the temperature gradient.
Yeah.
At the surface.
Yeah, and that's
So-
what I was starting.
That's what you were starting to do. Okay.
Because I guess the thing we know at the surface is it. Well, you know that DE, which
Yes.
E is our Q. So of a material, DE is equal to.
That's kind of hard to solve.
There, and so we can make a statement about what our.
This is not steady state.
Yeah, you need to.
What the surface temperature is relating to.
Well, it would be what the flux
Yes.
is at that
Well,
boundary.
well,
It's still a flux at that
yeah.
boundary. You're not going to
Yes.
convert it into a temperature because you don't know the temperature until you've solved the whole problem. So you will keep that as a flux boundary condition. You just need to write it in terms of a flux, which using Fourier's law is K dt dx at that location. So yeah, that's where you want to keep it as a flux, and and there's a version of this solved in the notes, so you guys can walk through the rest of the math. I want to just show you a little bit of the conceptual solution to this, so that everybody's kind of ultimately our Q will be related to the flux at that boundary. But so the version that's in the notes, just so that you guys can see the subtle differences, it's actually basically the same problem upside down. And there's a couple of things that I did a little differently, a similar type problem, but I did a little bit differently. I decided that the temperature at the surface is a cyclical temperature. So you had the cyclical heat flux. I had a cyclical temperature. They're both solutions. In the problem in the notes, Q is a constant heat flux, and that's geothermal flux. And the reason that I set it up this way, I think actually your way is totally fine. It just gets at it from a different way, and that's that we often measure temperature at the surface. So we actually have more often that's the number that we know. If we assume that the air temperature at the surface is going to match the ground temperature there. That's the main reason that I did that. But you might want to do the flux, because if you're really looking at the solar radiation part, then knowing the flux input as opposed to the temperature might actually be more useful. So that's a good alternative. We also don't know this d distance. With the flux at the bottom, we don't need to know it as critically, because we can just, if this is our x1 direction and this is 0, it's okay that we don't know the d, at which, I mean, we sort of assume that the q, the flux coming up from the bottom of the Earth is the same at multiple depths. I mean, obviously it increases as you go much deeper, but it's there at some depth. So those are really the main differences that are for the one that's worked out in the notes. Ultimately, the same equation that you just wrote, the rho c dt. Whoops, can't even write this. Equals d dx1 k d dx1, where k is constant. So yeah, that exact same equation. Here we have at t of 0 equals this, and q at some d equals, q, a constant. It's not that hard to work through it, but it does take kind of remembering some of your partial differential equation solutions. What does this look like? Any ideas what it looks like? Either of you?
It's going to be, if k is, let's see.
Yeah, you're
Something
you're
like
close. Yeah. So
Yeah,
we could even
it's gonna have to-
do your version of having a constant t at the bottom for a moment. So we have some temperature at some depth. In the summertime, hot, cold. In the summertime, the peak of the summer, if it might look like this, it might not exactly, but it might look like that. Peak of the winter, it might look like this. So the symmetry. If, though, the seasonal cycle is going a little bit too fast, it's not necessarily going to be able to reach. I mean, you could eventually, even if it were steady state, you would eventually end up out here, right? That would be, if you has super long cycle, say the Pluto's years, where you have forever to reach this temperature, then it would turn out to be a linear steady state solution. Steady state solutions are often linear, not always. In the middle, you could get something that looks like this. So it takes longer for this deeper part to catch up with the hot summer temperatures. So this is how you can have ice preserved a little bit down in our permafrost, even if it's way warm at the top. There's a lag. So if you're down a certain depth, say a meter in Fairbanks, you could have a lag where you actually melt the ice at the beginning of winter instead of at the peak of summer, because it takes time for this to warm up down below. So depending on your hot and your cold extremes compared to the temperature and how fast it's moving back and forth. A diurnal cycle, how deeply into the earth does a diurnal cycle affect temperature, do you think?
A few inches.
Yeah, not very far compared to the seasonal cycle, which digs way down. So the the daily cycle might be that's probably not even too much. It'd be like this.
Yeah.
So whenever you have a cyclical boundary condition, you're going to end up with some kind of pattern like this. And the depth, if you go down deep enough, then you really are at that T0. This is with snow. I'm sure you've heard of our famous 10-meter temperature concept with glaciers. If you haven't yet, you will very soon.
I actually have not.
If you go down 10 meters into a snowpack, certainly into the ice, but even the snowpack, you're at the temperature of the fern at that depth is pretty darn close to the average annual temperature at that site. Doesn't matter what day of year you go there, it doesn't matter anything, because it's down deep enough that you've got a little bit of wiggling back and forth maybe, but not enough to really matter. So if we drill a 10-meter hole, measured the snow or ice, we would be down in this area. Anything up above, and it could look like, many different versions of this. If you had, does that make sense? Did you have a question?
Yes.
Question.
So if you drill a hole, it means you make a hole, and like all the walls in that hole will get affected by the air temperature outside.
Yeah. So if you drill that hole and you want to make that measurement,
how to make it accurate, like the 10 meters.
It takes time for the air temperature. It's a beautiful sunny summer day. You drill the hole. It will be affected by that air, but especially if you have a reasonably small hole, it takes time for that air to circulate down and back up and affect it. So
you also have to wait a while after you drill, though, right? Because the drill would cause.
Good. Yes, that's a good point as well.
So you gotta
usually-
find that sweet spot where it's like not
I guess the
outside temperature,
ice,
but it's cooled up.
Like
yeah.
you'd have to heat up the ice around the walls as well, and so like that.
Because it's basically
It's difficult.
if the hole is small enough, it will prevent a lot of circulation. And then yes, you do have to wait. And we actually
wait.
did this when I had students drilling into waterfall ice down near Healy, and they took a 1/4-inch drill bit that was 50 centimeters long, drilled in, stuck a thermistor string in there, and then they looked through time to see after the heat generated by the drilling, but before you got it equilibrated much with the atmosphere, which didn't end up happening that
So they
much.
just kept track, and then they.
Yeah, they just measured the same thing. They
find
watched
the
it for about 10
point.
minutes and decided that it had settled down to the ambient, the ice ambient
I
temperature.
guess that makes sense. You just take a lot of measurements and then find one that's in the middle of.
Also, I will say, I just realized, thinking about our problem, there was a problem with setting up the problem on the moon, in that it's not, the input flux is not a perfectly sinusoidal function. It's kind of once you get to, I guess what you'd call astronomical twilight,
Yes.
it becomes kind of a step function.
That's true. That's true. The moon would look more like this. The Earth, we have.
Well, unfortunately, it's not perfectly step, because on the step up, there's many days of a step up kind of, as it like turns, and so
Yeah.
the actual input function would be.
So the other point I want to make, and I'm seeing we're going to have to get to yours on Tuesday because we got too distracted talking about this. If you did have, that one was just the constant temperature at depth here with the sinusoidal surface. If we do instead have that heat flux, so we have a hot, cold, what's different in this solution? What do you think would be different?
What are you saying?
Or do you think it would look the same?
So it's the surface is hot,
The
is cold
same
and hot at different-
sinusoidal cycle on the surface that we just had. The only difference in this problem is we have a geothermal flux instead of a constant temperature at depth.
Oh, as you get deeper, the temperature is constantly going up. Say the curve
Yeah, because remember, Q is equal to K dt dx. So what this is saying is that the gradient at some magic depth d is always constant, not the magnitude of that t. So it might look like where this is our dt dx. And so the same kind of idea would be going on with it cycling back and forth, but eventually you would get to a depth where it would have a fixed gradient. If you decided to increase your TH, but keep this the same, I didn't draw that very well. This would be the same dt dx, but now your TH is higher. This is our climate change version. We would actually shift the absolute temperature down at whatever depth we're interested in would shift, but the gradient would stay the same. So this is, this is actually what they see as happening in some of the permafrost boreholes in the North Slope, where they drill down hundreds of meters and they have temperature profiles within there. And as things warm up, as things are warming up, obviously there's a transient term there, but the end state with changing the temperature at the surface shifts the gradient, the whole gradient there. It shifts the slope. Because there is no fixed temperature down on the Earth. It's a fixed flux that we have because of radioactivity. So we often do use flux, but sometimes we use temperature as the bottom boundary condition when we're thinking about a problem, a ground problem like this. Either can work, you just have to be aware of how the difference in that bottom boundary condition will affect your ultimate solution. And if your bottom boundary condition is 100 kilometers away, then it might not matter which one you choose. You might get the same. If you're only interested in the top 100 meters and you put your boundary condition way, way far away, then you're not going to notice the difference in the two boundary conditions. But if your boundary condition is close enough to the area of your interest, then you will get a different answer if you put a different boundary condition on it. Does that make sense? These kind of seasonal or daily cycles are very common, obviously, in the earth sciences. One of the things that we use to describe these, so if we go back to kind of the more direct, nice there is, do you remember when we did our e-folding in the first lab? The e-folding time, or our tau, the Maxwell time constant, and how we said that 5 of those gets us most of the way to where we want to be. That's true of most e-folding kind of processes. This outer version, the envelope that this falls into for the steady state solution, is also just this curve is an exponential curve. There's all sorts of other things going on inside there, but the outer envelope that's shaped like that is an exponential, and so we can do the same thing where we call this a skin depth, where it's basically like given a frequency, how does that affect our skin depth? So diurnal, the skin depth might only be an inch. A seasonal cycle, the skin depth might be 10 meters as it is for ice. It's a little bit less for ground. Ice age cycles that skin depth might be hundreds of meters. So the permafrost temperatures in northern Alaska, you could do the same model thinking about the full ice age models in hundreds of meters deep in the rock. So given the frequency that you're oscillating the surface boundary condition and the properties of your material, you'll end up with a skin depth that is often, it can fall out of the equation, but one version of it is the square root of kappa tau, where kappa is our diffusivity, so it has the conductivity K, rho our specific heat, rho our density, and our specific heat. So that's that triplet of constants that affect the thermal properties. Tau is the period. Omega would be the frequency that we're thinking about, but tau is is the period that's doing. So that might be a year if you're doing annual cycles. So, cool. I think that's it. And I was just glancing through a bunch of your homeworks. I'm trying to get those back to you. I'm going to have looked at them by the time we meet tomorrow, the regular meeting tomorrow. And one person noticed that I put somewhere M over A, and I realized, is this yours?
I did.
Because I looked at yours first. You're like, I don't know what this is, but and I have to apologize because we use that in glaciology a lot. A stands for annum, so it's year.
Okay.
Some journals require us to use A instead of YR, so we end up using it a lot. So I'm sorry if that was confusing to anybody, and I won't take off points if it didn't work out to be the right.
I've seen MA, but I've never seen M over A. So that's
that
what
would
threw
be
me
a
off.
I said I thought it was A, but I wasn't entirely sure.
Yeah.
I
Sorry
think I've
about
seen this
that.
before.
But it didn't matter if you have a day or a year there. Whenever I converted, it didn't seem to affect the overall value too much.
It might